Hello, this is Dr. D. We're going to be talking about electromagnetic radiation or light in this video. Before that, let's start talking first about energy. And you no doubt heard about the law of conservation of energy, where energy can neither be created or destroyed. Rather, it can only be transformed from one form to another. Energy is the capacity to do work or to transfer heat. And all forms of energy are either kinetic or potential. So let's talk a little bit about kinetic energy. It's the energy of motion. So if E sub k is kinetic energy, it's equal to 1/2 mu squared, where m is the mass of an object and u is its velocity. For chemists, thermal energy is the energy associated with the random motion of atoms and molecules. So that's the form of kinetic energy that we'll be most interested in. Potential energy is energy possessed by an object by virtue of its position. And so one form of potential energy is when you have an object that's been raised to where it's further away from the center of the Earth. It's got a greater potential energy due to gravity than something that's closer to the Earth. But for chemists, we're really concerned about potential energy that's stored within molecules. Chemical energy is stored within the structural units of chemical substances. There's also electrostatic energy that we're interested in. It's the potential energy that results from the interaction of charged particles. So this equation shows you that electrostatic energy is proportional to the two charges divided by the distance between them. So as you increase the distance, you lessen the electrostatic attraction, electrostatic energy, or as you increase the charges, it would be increased. So let's talk about the units of energy. The SI unit for energy is called the joule. It's named after the English physicist that you see, James Joule, who lived in the 1800s. So if we go back to that equation of 1/2 mv squared, mu squared, mass, the units of mass are kilograms, the SI base unit, and velocity is meters per second. But if you're going to square that, you wind up with the kilograms times meters squared divided by second squared. That's equal to a joule. A joule is really very small, and so in practice, what we'll be using are actually kilojoules. Remember, the SI prefix kilo means 1,000, so 1 kilojoule is equal to 1,000 joules. So let's get on to what this video is really about in this light. And we're most comfortable, we're most familiar with visible light. It's actually only a small component of the radiant energy that's known as the electromagnetic spectrum. The electromagnetic spectrum refers to the electromagnetic radiation, where we have an electric field and a magnetic field that are propagating through space at right angles to one another. We're going to talk about the electromagnetic spectrum in more detail a little bit later in this video. To understand light, there's not a unified theory that explains it. There are actually two ways of trying to understand light. When you put them together, you get a picture of how light behaves. And so we can refer to this as the duality of light. And that we can think of light as either being waves, or we can think of light as being particles. So if we think of the properties of waves, we can talk about the wavelength and the frequency. So wavelength is symbolized by this Greek lowercase l called lambda. It's the distance between identical points on successive waves. So from crest to crest, or from trough to trough would be examples. Frequency is symbolized by the Greek letter nu. It looks like a V, but it's really a Greek letter nu. And it's the number of waves that pass through a particular point, in 1 second. Amplitude is the vertical distance from the midline of a wave, the top of the peak, or the bottom of the trough, the depression. As we're going to be talking about light, we're going to be talking about wavelength, lambda, and frequency, nu. And you've actually heard of AM and FM frequencies on the radio dial, which refer to amplitude modulation and frequency modulation. So one of the ways that waves behave is how they can interact with one another. You can sort of think of the waves that are created when you drop a pebble into the water. Or you can think of it as when you drop two pebbles side by side, these waves that start coming out, they're going to interact with one another. And so the way they interact, they can either show constructive interference. That's when the waves are exactly in phase or in sync, and they add to one another. So the two smaller waves, the blue wave and the red wave that you see, combine to make this larger green wave. That's constructive interference. That's when they're exactly in sync. Or they can be exactly out of sync. They cancel one another out. It's called being out of phase, and that's destructive interference, where the blue wave and the red wave that you see cancel one another out, make this green straight line. And they can be somewhere in between also, partially constructive and partially destructive, but these are the two maxima. And so there's this famous experiment that's called the double slit experiment. We can send some light through a pinhole and then send it through two other pinholes, and these wavefronts are formed, and they'll interact with one another to constructively and destructively interfere. And you can see the patterns of light as this green laser beam hits that final screen. So where the green bands are is where constructive interference is taking place. Where the dark bands are is where destructive interference is taking place. Where they're out of sync, they're canceling one another out. So let's do some calculations involving waves, particularly light waves. And so if we take nu times lambda, that will equal to velocity. And if we're talking about light, that velocity is going to be the speed of light. The speed of light is 3.00 times 10 to the 8th meters per second. That's the three significant figures. And so let's do an example. Let's talk about a microwave oven operating at, say, 2.54 gigahertz. What is the corresponding wavelength? And so this is like the microwave oven at your house. So if we rearrange that equation up at the top, do a little bit of algebra, lambda will equal to C divided by nu. So 3.00 times 10 to the 8th meters per second divided by 2.45 gigahertz. Now remember, giga is an SI prefix that means 10 to the 9th, or a billion of them. And hertz is another way of saying reciprocal seconds, or 1 over seconds. And so now we have meters per second divided by 1 over seconds. The 1 over seconds in the numerator and in the denominator cancel out, so we're left with units of meters, which is what we were after. So the wavelength for a microwave in your oven is 0.122 meters, or that'd be 12.2 centimeters, or just under 5 inches. So that's how we can convert from frequency to wavelength. And you need to be able to go in the opposite direction from wavelength to frequency. So here's the electromagnetic spectrum. We can show the different types, labels of electromagnetic radiation, and noting the wavelength and the frequency. There are also some pictures of what those particular bands of the electromagnetic spectrum can do for us. And so on the left, these very high energy rays, gamma rays, and they come X-rays, and we use X-rays in the clinical setting. And you can see the picture of somebody's hand there. And ultraviolet lights, and then the visible, then infrared, then microwaves, then radio waves. And so if you look at the wavelength as we go from left to right, we're going from 10 to the minus 3 nanometers to 10 to the 13th nanometers. So now we're actually talking about meters in terms of length. And so as we go from left to right, the wavelength is increasing. If we look at the frequency going from left to right, we're going from 10 to the 20th hertz, or reciprocal seconds, down to 10 to the 4th hertz, or reciprocal seconds. And so if we go from left to right, wavelength is increasing, frequency is decreasing, and then if you look at the type of radiation, the energy of those, as we go from left to right, the energy is decreasing. So frequency and energy are directly related, they're directly proportional to one another. Whereas wavelength and energy are inversely proportional to one another. We try to stay away from gamma rays and X-rays. They're types of ionizing radiation that can cause cancer, for example. For that matter, we put on sunscreen to keep away the UVA and UVB rays. There's a high energy. If you get a CAT scan, you're actually being scanned by X-rays, and so we try to limit those CAT scans, very much so. We'd much rather, if possible, to use as a diagnostic tool, would be MRI, magnetic resonance imaging, which actually uses radio waves, which are not ionizing. And so there's some real-world examples for you about the electromagnetic spectrum. So we talked about light as behaving as waves. We can also kind of talk about light as behaving as particles. And so Max Planck got the 1918 Nobel Prize in Physics for helping us along with this understanding of the particle properties of light. And he arose out of the early attempts by the 19th century physicists to figure out the structure of the atom. And it met with only very limited success. And they were using the laws of classical physics that involved the macro world, the world that you could see. But what we really needed to do is look at this nano world, the sub-nano world, actually, this atomic world, the subatomic world. And so over time, they came to realize, except that the behavior of subatomic particles is not governed by the same physical laws as larger objects. And so Planck talked about the quantization of light. So there's Planck's constant, which is equal to 6.63 times 10 to the 34th joules times seconds. That's Planck's constant. Don't worry about memorizing it. If I give you a quiz or a test, I'll certainly give that to you. It says, famous equation that he came up with is that energy is equal to h nu, where h is Planck's constant and nu is the frequency. And so if you look at those units, h is the units of joules times seconds. Frequency is 1 over seconds. And so seconds times 1 over seconds cancels. You'd wind up with units of just joules, which is a unit of energy. So the idea that energy is quantized rather than continuous is like walking up a staircase or playing the piano. So let's look at that, what we mean by quantized. When you hear about a quantum leap, it's not that quantized doesn't mean that it's large, just that it means it's discrete or separate. And so you talk about pouring sugar. If you think of sugar as units of energy, as you pour it out, that's more or less a continuous amount of energy that's being delivered. Whereas instead, if you use sugar cubes, you're dropping these quantized or individual sugar cubes one bit at a time into your coffee cup. So that's the difference between continuous and quantized. A ramp versus steps. If you look at it in terms of height, going up the ramp, as you go up the ramp, you can be at 6 inches off the ground, or 8.2 inches off the ground, or 24.3 inches off the ground, depending on where you are along the ramp. However, if you've climbed the steps, and let's say the steps are 6 inches apart, you can only be at 6 or 12 or 18 or 24 inches above the ground. Quantized is the ramp. Continuous is the ramp. Quantized are the steps. Or playing the guitar, the notes are there quantized, are there continuous. We can slide your finger up and down the string, give you different pitches. Whereas when you play the piano, that's quantized. You can only play those notes that correspond to the keys. And so Einstein used Planck's theory to explain the photoelectric effect. And for this, he won the 1921 Nobel Prize in Physics. The photoelectric effect is when you shine some light on a certain type of material, typically a metal or a semiconductor. If it is of the right wavelength or frequency, which means it has the right energy, it can cause that metal to eject an electron and cause a current to flow through this photocathode that you see to the right. The electrons are ejected from the surface of the metal as long as it's above a certain frequency, what we call the threshold frequency. You can shine as intense light as possible as you want it, as many photons, but if it's not the right energy, nothing's going to happen. But as soon as those individual photons have sufficient energy in and of themselves, you can cause an electron to be ejected. This is the photoelectric effect. I wish they called it the photon-electron effect, but they didn't. It's the photoelectric effect. A photon strikes the metal or semiconductor and it causes an electron to be ejected. So Einstein is actually the person who coined the term photon, and it's for this that he won the Nobel Prize. It's not for general relativity or special relativity. It's for the photoelectric effect that he won the Nobel Prize. And so once you've reached past that threshold frequency, the more photons you have, the more electrons that will be ejected. The greater the current will be. But until you get those photons that are energetic enough, nothing will happen. For example, if that metal were, say, potassium, you can shine red light on it as much as you want, as intense as possible. Nothing's going to happen. But if you boost that frequency up, lower the wavelength to where it's yellow, it can cause electrons to be ejected in a flow of current that we call the photoelectric effect. So below that threshold frequency, nothing happens. Above it, the photoelectric effect can happen. So line spectra are the emission of light only at specific wavelengths. And so Bunsen and Kirchhoff in 1859 discovered that when you put different metal salts into a flame, we knew they gave off different colors, but using this prism, they were able to determine that they were particular frequencies, particular colors. And so different elements have their own unique emission spectra. And so lithium, you can see the red line to the left. It's the brightest one that you can see if you're seeing the lithium emission take place. And an example of emission would be watching fireworks. We've added energy to these metal salts, and you're watching those excited atoms go back down to the ground state and give off a photon of light. We'll be talking more about that a little bit later. The sodium, the doublet, the two yellow lines are very intense. And barium, if you look toward it has all sorts of different lines along it. And the hydrogen, helium, etc. In fact, we discovered helium during a solar eclipse. When J.N. Lockyer used a spectroscope to look at the solar corona, he noticed some lines that had not been detected before. And with that, he knew he had a new element. And so he named it helium, which comes from the Greek word helios, which means sun. So here are the hydrogen emission lines that you see in the top photograph. And so emission is when light is being given off. The atom has been heated up, it's gained energy, and it has to release that energy. And it's doing so by emitting light. In a like manner, you can also look at an absorption spectrum, where if you show white light on a sample of hydrogen gas, you can see where it absorbs energy. That's related to those dark lines that you see, and they're the exact same wavelength as are the emission lines. So in emission, the atom has gained energy thermally, and then given off that heat by giving a photon a specific wavelength. Or you can excite it. You can have absorb light at that particular wavelength and pull that light out from the white light that's bombarding it, the sample. So that's a little bit about electromagnetic radiation. We'll be talking more about our understanding of how the atom is put together that will help us to understand some of these concepts that we've been using and learning thus far. Thanks for listening.